Hello everyone, welcome back. In this module, we will discuss about BGP, EVPN route types 1 and 4. But before we discuss EVPN route types 1 and 4, it is very important that we discuss multi-homing. So as the name implies, multi-homing is a method wherein we attach an endpoint or a switch to more than one upstream device, which is a very common practice in any network scenario, be it an enterprise network or a service provider or with a data center network. Again, this is done to provide load balancing and ensure failover in case of a link level or a node level failure. It is very common to see an end host or a switch to be connected to two upstream switches. The number of upstream switches could be more than two, but again, it is a common practice for a top of rack switch or a server or a load balancer to be connected to more than one, or let's say two upstream switches in a port channel configuration. From an implementation point of view, it is a very vendor specific space. So various vendors call this technology with vendor specific or with bespoke names. For example, in case of Cisco Nexus portfolio, we call this technology as VPC or virtual port channel, or in case of Arista, it's called the MLAG or multi-chassis lag. But the technology in general is called MC lag or multi-chassis link aggregation. In most cases, MC lag or multi-chassis lag is implemented or limited to two devices only. However, EVPN overcomes this restriction and provides support for all active redundancy. So we can say that EVPN multi-homing is the standard or the open standard version of MC-lag, but it provides much more than that and can also be seen as a replacement for MC-lag. And some of the points where it differs from MC-lag can be seen as below. So it eliminates the need for peer links or interswitch links between the top of rack uplink switches. So if we look at this topology with VPC or MC lag, the uplink leaf switches or the uplink switches need to be connected or interconnected with a peer link, but EVPN eliminates the need for the uplink switches to be interconnected via this peer link. For example, Nexus VPC or Arista MC lag has this requirement that the peer switches need to be connected via the port channel, which is called the peer link. With EVPN, there is no need for the interswitch link between the members of the VPC or MLAG. Also, EVPN allows for more than two top-of-rack switches to participate in a port channel configuration or in a redundancy group. If we take a look at this topology again, we are not fixed with two uplinks. So we can now have the endpoint connected to leaf 1, leaf 2, leaf 3, and they will be part of the same Ethernet segment as it's called in the VxLAN architecture. And we will discuss more about the Ethernet segment going forward. Also, EVPN provides a single BGP EVPN control plane, and we will discuss this point in detail going forward. And as we are using BGP for our control plane, it allows for multi-vendor interoperability. And just to prove the significance of multi-homing in EVPN, it's so important that there are two route types that are dedicated for multi-homing, namely EVPN route type 1 and EVPN route type 4. So friends, before we discuss multi-homing any further, let's discuss some important considerations regarding multi-homing. So the first point we must consider is, so what are the available ways for a host or an endpoint to be dual homed or multi-homed rather? I'm pretty sure you must have guessed the answer to this question. So if you're thinking something on the lines of MLAG or VPC, yeah, you're going in the right direction. Also, the second thing that we must consider is that in a redundant environment, how is a dual attached host seen by other remote VTEPs or remote leafs? For example, if we look at topology, how will PE4 or leaf 4 look at endpoint 1? So how does PE4 know that endpoint 1 is connected to more than one upstream leaf switches, or upstream VTEPs in this case? Also, we must consider how bump packets are delivered to an endpoint in a multi-homed environment, and then how network redundancy is maintained when one link fails for dual-homed or multi-home endpoint. These are some of the important considerations that we will discuss going forward in our discussion regarding EVPN route type 1 and EVPN route type 4. So friends, coming back to the first point regarding what are the available ways for host or an endpoint to be dual homed or multi-homed. So as discussed previously, one of the first or the obvious method is MLAG or MCLAG or VPC as we call them, or let's say the vendor specific method for dual homing a device. In most scenarios, we have two links from the endpoint or top of rack switch connected to the uplink aggregate switch, or let's say from a server to two separate top of rack switches. And these links could be configured in an active active or active standby load balancing method. And on the server or the endpoint, we have a single IP that's used. So for example, if it's a server, we typically configure nick teaming on the server and give it an IP address. Or if it's a switch, we typically create a port channel and give it an IP. So if we go back to our topology, so let's say if this is our endpoint or the server, we will usually have a port channel going towards leaf 1, leaf 2, and these leaf 1, leaf 2 would be interconnected via a peer link. And yeah, this is either going to be MLAG or VPC towards the endpoint. The other method for multi-homing is BGP EVPN, also called as EVPN ESI, which stands for Ethernet Segment Identifier. It's very important to note that BGP can facilitate multi-homing natively via EVPN, and EVPN primarily uses route type 1 and route type 4 to handle multi-homed devices. And like in MLAG or MCLAG, EVPN multi-homing supports two modes. So it can be active-active or active standby. But a very important distinction is that BGP EVPN is not restricted to two links in the bundle or in the port channel. So if we add a third link towards a third leaf switch, for example, endpoint 1 connected to PE3 or leaf 3, that is a totally supported topology. So friends, before we discuss how route type 4 works, let's quickly have an overview of the EVPN operation in general. So as soon as we configure a VNI or a VLAN to a VNI mapping on a leaf switch or a PE switch, the leaf switches start the process of discovering the other leaf switches that are part of the same VPN. So as we are stretching a layer 2 broadcast domain or bridge domain across a layer 3 backbone, the leaf switches need to know who are the other leaf switches who are participating in the same VPN, or let's say who have the same VLAN to VNI mapping configured. So this is done through EVPN route type 3, or as we call it, inclusive multicast Ethernet tag route, or in short, they are called IMET routes. If you're unclear about route type 3, I would highly recommend you to go and watch the previous video, which covers EVPN route type 3 in detail. So in a multi-homing scenario, the PE routers need to auto-discover the remote PEs and their corresponding redundancy mode. So in our topology, PE1 or leaf 1 needs to know that EP1 or endpoint 1 is also connected to PE2 and PE3. So they are part of the same Ethernet segment. So they are part of the same bundle from endpoint's perspective. From the leaf switch point of view, these set of links, it's called Ethernet segments. So if you have to define the term Ethernet segments, it's the set of links connected from the customer edge device to the set of multi-homed provider edge device. So from the point of the custom edge device, it's basically a bundle link or aggregation link. But from the provider edge device or the leaf switch, it's we call it as an Ethernet segment. And each Ethernet segment is assigned a 10 byte non-zero value, and this 10 byte value is called an Ethernet segment identifier. So it identifies the Ethernet segment in the EVPN topology or in the EVPN network. So as soon as we configure the Ethernet segment on the interfaces towards the customer edge, the PE devices or the leaf devices would send route type 4 towards the spine routers, which are also the route reflectors in this case. and the spine routers will reflect those BGP update towards the other leaf switches. And once PE2 and PE3 receive this BGP update from the route reflectors, it can establish that endpoint 1 is a multi-home device. So there are primarily two functions of Ethernet segment route or route type 4. One, to discover other ESI members or other PE routers connected to the same Ethernet segment. Secondly, it's used for the designated forwarder election, which we will cover in a little while. Let us now discuss how does a PE router discover other multi-homed PE devices. So as we know that when we are talking about these PEs, they do not have an inter-PE or any links connecting between them like we have in the case of VPC or MLAG. So this is where route type 4 comes in. So this discovery is done through a process or an attribute called ESI or Ethernet Segment Identifier. So each of these leaf switches or PE devices would have a unique ESI or Ethernet segment value configured on the link connected towards the endpoint. So for example, if we configure this endpoint or link connected to EP1 as a value of 100, likewise on this link we give it a value of 100 and same as on PE3. So based on this Ethernet segment identifier or Ethernet segment value, the leaf switches will generate a unique import route target, and when the route type 4 is advertised towards the spines and the spines send this route towards the other PE devices, and once those PE devices receive the BGP update with the import route target, they can either discard or accept the NLRI. So in this case, when PE1 sends the BGP update towards the spine and the spines reflect this BGP update towards the PE2 and PE3, so as PE2 and PE3 have the same Ethernet segment configured, and would have generated the same import route target value, they would accept this NLRI coming from the spines. And this is how PE2 and PE3 will know that endpoint 1 is multi-homed. Also, the other thing that one might think is what happens when the PE devices that do not have the same Ethernet segment configured receive this advertisement from the route reflectors. So as the route reflector will send this advertisement towards PE4 as well, as PE4 does not have the same Ethernet segment configured, it won't have generated the import route target, so it would discard that prefix or that NLRI. And secondly, we use Ethernet segment route or route type 4 to elect a designated forwarder per Ethernet segment. So friends, let's quickly discuss why do we need to elect a designated forwarder in the first place. So let's say endpoint 1 wants to send some traffic towards endpoint 2 and it does not have the ARP resolution for endpoint 1 at this stage. So endpoint 2 in this case will generate a broadcast packet which will be received by PE4, and as it's a broadcast packet it will be sent by PE4 towards all the other PEs that are participating in the same VPN or the other leaves who have the same VLAN to VNI mapping configured. So this broadcast packet will be received by PE3, by PE2 and by PE1, and subsequently as these PEs have an endpoint in the same VLAN, they would forward this frame towards endpoint 1. This way endpoint 1 will end up receiving multiple copies of the same broadcast packet. This is why we need a designated forwarder and a non-designated forwarder in the topology. So when a non-designated forwarder receives a packet for a connected endpoint, it discards that packet to prevent loop in the network. So let's say if we say PE3 is a designated forwarder in our topology, and PE1, when it receives the broadcast packet from PE4, as it needs to be sent to a connected endpoint, it will drop that packet. Likewise, PE2 will do the same thing, and it will drop that packet, and which will prevent a loop in the network. The designated forwarder, which is PE3 in our topology, will forward that traffic towards endpoint 1, preventing endpoint 1 to receive multiple copies of the same broadcast packet. Also, what happens when endpoint 1 generates some bump traffic and it needs to be sent to the other side, or PE4 in our topology? So endpoint 1 isn't aware that it's connected to 3 different upstream switches, as from its point of view, it will have a bundle configured towards the leaf switches, and it will see the upstream leaf switches as one device. So this traffic from endpoint 1 could be hashed to any of these links. So it could be PE1, PE2, or PE3, depending on the hashing algorithm. So what happens when a non-designated forwarder receives this bump traffic? So when the server or the endpoint sends the bump traffic and it gets hashed to the non-designated forwarder, the non-designated forwarder will flip a bit called split horizon bit before sending the bump packet towards the other VTIPs. So let's say if PE1 gets this packet and it sends the broadcast towards the other VTIPs via the spines, it will flip the split horizon bit, and when this broadcast traffic gets to the designated forwarder will receive this broadcast packet with the split horizon bit flipped, and it will not send this packet towards the same Ethernet segment on which it was originally received by the non-designated forwarder. So in this case, the non-designated forwarder will play the role of a designated forwarder. And in terms of the contents of route type 4, the most important element it contains is the Ethernet segment identifier and the next hop IP address. So with these two values, the receiving leaf switches will know which are the other leaf switches that have the same Ethernet segment configured. And this ESI value that we discussed previously is based on the MAC address of the server or the connected endpoint. So guys, I'm going to quickly walk you through the contents of route type 4. So this is the topology that we'll be working on. So we have 3 leaf switches connected to 2 spines in a redundant manner. And then we've got VLAN 10 client 1, which is connected to both leaf 1 and leaf 2. And then we've got host 1, which is again another client in VLAN 10. And then we have another client in VLAN 20 to check inter VLAN connectivity. So just to go over the contents of route type 4. So when the leaf switch, in this case leaf 1, sends the update with the route type 4 towards the spine, these are the contents that we get inside the advertisement. So the first field is the route distinguisher, and then like previously mentioned, the important field is the ESI system MAC, and it also contains the IP address length and the IP address of the originator, which is leaf 1 with an IP of 3.3.3.3 in this case. And in terms of the route target that was mentioned earlier, so when we configure the Ethernet segment on our interfaces towards the customer edge device, and the way we do it is, so in terms of configuration, the Ethernet segment value goes under the port channel towards the customer edge device. So we define the Ethernet segment identifier along with the system MAC. Also, as a prerequisite, this command needs EVPN multi-homing code tracking enabled on the link towards the spines. So these are my interfaces towards the spines, and I've got the EVPN multi-homing code tracking enabled. It also needs the EVPN multi-homing feature enabled globally, and this is the command to do it, EVPN ESI multi-homing. And if you look at the CLI, the update that it received from Leaf 2, which has an IP of 4.4.4.4, so when it received the update, it had the root target value of all zeros and ending with 10. That's the auto-generated import root target. And this leaf itself generated the same root target. So if we look at this value extended community, so it has a root target of all zeros ending with 10. So that's how PE routers discover each other. So when they receive this import root target via the BGP update, this is how they know that yes, there are other PEs that are connected to the same Ethernet segment as itself. And regarding the DF election part, as in which router or which leaf switch becomes the designated forward and which switch becomes the non-designated forwarder or forwarders, there is a mechanism that runs between the leaf switches which decide which switch will become the DF and which switches will become the NDF. It is done on a per VNI basis. It is a quite detailed process, but in short, it is based on the lower MAC address. I'm sorry, the lower IP address. So whichever switch has or whichever leaf has the lower MAC address will become the designated forwarder for that VNI. So friends, let's now quickly go over EVPN route type 1, which is also called Ethernet Auto Discovery Route. Why is this route type called Ethernet Auto Discovery Route? To answer that question, let's look at the same topology that we've been working on so far. So in this topology, how does the remote PE or the remote leaf know that the endpoint at the remote side is connected to more than one leaf switches or more than one PEs? This is where things might get a bit confusing because with route type 4, the PEs discover other PEs that are connected to the same endpoint, and with route type 1, the remote PE discovers or figures out that a remote endpoint is connected to more than one leaf switches, so it's multi-homed. So this is where we use Ethernet Auto Discovery Route or route type 1. So as soon as we configure an ESI value on a leaf switch, it sends out the Ethernet auto discovery route or route type 1 towards the spines. So likewise, this process is done on PE2 and PE3 the same way. So PE2 and PE3, they will send this route type towards the spines, and the spines will reflect this route type towards the remote PE, which is PE4 in our case. So the remote leaf now has an ESI value, ESI entry, and it knows that to get to this particular ESI, it can take PE1, PE2, or PE3. So now when endpoint 1 sends any traffic towards Ethernet segment, for example, it sends a gratuitous op towards PE1. So it has now come up. It shows this link towards PE1 using the hashing algorithm. And then as soon as the PE1 receives the gratuitous op, it sends a route type 2 towards the spines, which are the route reflectors in our topology. And as they are route reflectors, they will reflect the route type 2 towards the remote PE as well, which is PE4. And as this route type 2 also contain the Ethernet segment identifier, when the remote PE learns this ESI, it can check that this particular ASI can be reached via PE1, via P2, and via P3 as well. So now when the remote PE, P4 in our example, needs to return the traffic or needs to send the return traffic towards the endpoint 1, it can choose any of these remote PEs or PE1, PE2, or PE3 in our case. So this is how load balancing is performed using Ethernet Auto Discovery Route. So we can see that the ESI value that we configure on the leaf switches plays a very vital role in ensuring load balancing across the underlay fabric. And this process is also called as aliasing in EVPN network. So aliasing is the process or the feature that provides the leaf switches with the capability to load balance layer 2 unicast traffic towards all multi-homed PE devices that have the same Ethernet segment configured. Also, when you talk about Ethernet auto discovery route, there are two types or two variations of them. We have an Ethernet auto discovery route per Ethernet segment, or we have an Ethernet auto discovery route per EVI or per Ethernet virtual instance. So in our topology, we have an endpoint as a server, but this endpoint could be a switch, and that switch could have multiple hypervisors connected, which could have multiple VMs running on them. And those VMs could be running on different VLANs, and as we know, the VLANs could be mapped to different VNIs, which represent an EVI in the EVPN topology. So on this very ESI, there could be an ESI for VLAN, let's say 100. There could be another ESI for VLAN 101. So with the help of Ethernet Auto Discovery Route, the local leaf switch could advertise to the spines about all the various EVIs configured on this local segment. And also route type 1 helps in faster convergence. For example, if PE1's interface towards the endpoint 1 goes down, it now needs to send an update towards its BGP peer and advertise a withdrawal for the MAC addresses learn on this interface or on this Ethernet segment. And as these MAC addresses and host IP addresses learned on this Ethernet segment or would be advertised to the spines as a /32 or an individual MAC advertisement routes or route type 2 in EVPN network. So these withdrawals can be done on a per Ethernet segment basis. So it will just send a single update towards the spine, sending that, okay, my link towards this Ethernet segment has gone down. And with that, all the routes or all the MAC addresses slash host IP addresses learned on this Ethernet segment could now be withdrawn. So we're talking MAC addresses and host IP addresses here. So we can't really summarize MAC addresses or /32 IP addresses. Hence, instead of sending multiple withdrawal updates towards the spines, it will send a single BGP update towards the spine, confirming the withdrawal of all the MAC addresses learned on this particular Ethernet segment. And in terms of the contents of route type 1, it is sent from the leaf switches towards the spines as an NLRI, which means that it will contain all the BGP path attributes like the local preference, AS path, weight, type, code, etc. And it will also have the Ethernet segment identifier. And in this case, as it's a multi-homed device, it will have a non-zero 10 hex value. And the next hop will be the loopback IP address of the leaf switch itself. So if we check this Wireshark capture, so we can see that it is a route type 1 sent from the leaf switch, which is in our case is PE1. So it contains the route distinguisher, the ESI value, which we configured manually on the port channel towards the VLAN 10 client 1 or the endpoint. So it's a 10 byte non-zero value. So if it were to be a value which contains all zeros, it would have meant that it's a single home device. And it also contains the BGP extended community, which is VNI in our case. So friends, this was a very detailed overview of EVPN route type 4 and EVPN route type 1. I hope you liked this video. And if you did like this video, please share with your friends and colleagues. And if you have any feedback about this video, please leave it in the comment section below. And if you are new to this channel, please subscribe this channel for any upcoming videos. Thanks for your time today, and I will see you in the next video. Thank you very much.